It's great to be here. It's great to be an invited speaker at AAPT. This has not happened to me so many times, so it's I first need to thank David Rosengrant for inviting me to be here. Normally I'm in front of the green screen in my house, but that didn't quite work out for today. My wife is actually about to have a baby any day now, and so I'm going to do the best I can with this talk. But I'm really excited to tell you about buckeyevr, which is a project that started a couple of years ago. And so we have a couple different things to share in terms of fun stuff that we've made. So why do you want to do VR? I'm probably preaching to the choir here, but the world is in 3 dimensions. If you look at most of our physics textbooks typically describe problems in 2 dimensions. And so it'd be nice to be able to have tools to be able to go to that 3rd dimension for certain problems that are intrinsically 3-dimensional. And the depth perception that you get from virtual reality, so if you look at in the top corners of this slide, you'll see that there's a smartphone there that has a split screen display, so each eye can see a slightly different view. Well, that allows the images to kind of jump off the screen, just like one of those view graph things that many of us played around with when we were kids. Chris Porter and I are sort of have been in many ways the leaders of buckeyevr, but I have to mention Dr. Joseph Smith, who wrote most of the software that we use and participated heavily in the research studies. We also have friends in the math department and the chemistry department at Ohio State, and people at the IT there. There's an undergrad, Sava Madar, helped to build some of those prototypes. The basic idea of what we're doing is that we have these example visualizations that we've coded up in an interface called Unity, which is built in C#. And through that, we can export it not only to the phone for the cardboard, but we can also have it export for the web so you can view it on the computer, even without downloading anything. Theoretically, we could export it to the Oculus Rift, because Unity allows you to do that. I mean, there's entire video games that are made in Unity, and the reason they like doing it in Unity is because it allows you to do Android and iPhone and Oculus and computers and all that stuff. And so they've done all the work. We just make the visualizations, then we export it to different platforms. So what I want to do first is I want to talk about our electric field app. And so if you go to buckeyevr.osv.edu, you'll find 2 links to the Android and the App Store. Right now our Android link is down, but you can still download what's called the .apk file. And so if you allow external sources on your phone, you can do it that way. So you can download the app, or you can just sort of click this icon on the left here, the buckeyevr icon here on the page, and that will send you to the computer view that allows you to see the same visualizations in your browser. Now in your browser they're not in VR, but if you're in front of the class and you want to point some things out, then that's an extremely helpful thing to do. So this is a single point charge in buckeyevr. And so I can click this interactive and open this up. So it'll just pop up in a second here. And I didn't have to install anything first, I should say. So there's no plugin that you have to install. It uses something called WebGL, which every browser has installed. And so if I press Alt, I can move this over here, and I can view the electric field of a single point charge. There we go. So I can sort of move that around. I can make it full screen, which is nice. So there you go. So I like this because we show the point charge and we show it's this thing in the middle with all lines coming out. But we rarely do we show like the full 3D nature of the thing. Now there's limitations to that, right? So you can ask students, all right, in the middle of these lines, what is the electric field? And you hope that they don't say 0, but you can address that specifically. So I like this image. The next one I want to highlight is, let's see if I can do. So there's a positive line charge, which is nice. Yeah, so I guess you're not supposed to click, you're just supposed to hold Alt. So you can kind of move this around. And so, students may not necessarily have seen a line charge like this before, but it kind of helps them to visualize that. You can see electric fields pointing away from it. That's nice. You can see a negative electric charge. So you'll notice that all the arrows are pointing towards the center, which is good. So that's another visualization that we have. It's in fully 3D. And my favorite one is the electric dipole. And there's a little bit of art in the science here because we had to decide exactly where to put the arrows. And so you can kind of see there's some arrows in the middle that nicely show that the electric field goes from the positive to the negative. What I think is cool about this demo is that the electric field over here is really strong, actually, and I think I didn't quite appreciate just how strong the electric field is right over here by the positive charge. Same thing over here by the negative charge where it's pointing towards the negative. So I just, it looks cool enough in the computer, but what's great is that the phone can view this too. If you download the app, the student gets to see this, and all these arrows kind of jump out at you, and you can kind of intuitively tell which ones are closer to you and further away. And the next thing I want to talk about is the plotter, and the conundrum. So the conundrum of trying to create these visualizations is that if you wanted to create something simple like a helix or a vector field or a contour, just something that's really not that outlandishly complicated, you are going to have to learn to use Unity. You're going to have to figure out how to code C#. I'm a C and C++ programmer. I still find C# to be kind of confusing to me. And then of course there's all the visualization commands and how to export it. There's a lot to learn, and I think anyone who's used Unity will agree with me that the learning curve is pretty steep, to be honest. And so what we did is that we said, well, what if we created a web page with our own little script that you could plot whatever it is that you want in 3D, and then have a mechanism to allow you to do that on the phone. And so that's what we did. And so there's this script that you can modify and add as much as you want to. You click render and you can kind of see what it looks like. So if you go to the buckeyevr page, this is our plotter thing. And then what you do is you click generate QR code, and something like this will pop up. And so now what you can do is you can, if you've downloaded our app on your phone, and by the way, all of our apps are free, the app opens up and it sort of activates your camera. You can take a picture of this QR code and then you can see it on your phone. And not only can you see it on your phone like this, you can click a button and see it split screen like that. And so each eye gets a slightly different view, and things really do jump out at you. And so, for example, this helix thing, it's a little hard to see which side is in front of or behind that line, but when you're looking at it in stereoscopic 3D on the phone, it just looks great. It's just, there's a lot of problems that really take advantage of this kind of really take advantage of that technology. So you can do all kinds of crazy stuff with this. You can do vector fields, you can do contours, whatever you want to do, it's capable of doing. It's not perfect, but it works pretty darn well. Other stuff that we have but have not had the time to publicly release, there's a link to the bottom where you can download this thing. So we have some visualizations that I've used personally in my introductory physics classes, E&M classes. So this is a good Gaussian surface, and you can see the electric field arrows there. This is a bad Gaussian surface that is closer to the line charge on one side. Further away on the other side, you can see electric field is a little stronger on the left because the arrow is longer. You can see that it's misaligned with the area vectors. Here's the Gaussian surface that is even less useful because it's not enclosing it. And you can see that the field is not, you can see that the field is not parallel to the area vectors. The strength is not the same. So we often say this with words, but again, the spirit of this is, instead of saying it, I want to show you it. And then here still is a third Gaussian surface that's not very useful. This one's a more subtle one because you kind of have to understand that, on the edges of the cube are a little further away, and so those electric field strengths are not quite as much. And then you have this angle with the area vector. And again, if you integrated this thing, it would integrate up to the same amount of charge enclosed, but it doesn't necessarily mean that it's useful. It doesn't mean that that integral is straightforward to do. So again, in the spirit of showing them instead of telling them, this is what we came up with. We haven't yet published this on the App Store, but it's something that you can download yourself. We do have some things on magnetostatics that I hope we can eventually release as well, but I didn't quite get time to prepare that today. So I use these in my intro E&M class to teach Gauss's law and to teach electric fields. Just sort of, I don't do a whole lot quantitative. I just sort of say like, well, here's qualitatively what I'm saying. There is a math professor at Ohio State that uses this stuff with Calculus 3 classes when you get into vector calculus. Some of that curriculum is connected to a group called Chimera, and so if you're interested in Calculus 3 materials that connects to this stuff, I'd be happy to talk about that. Bart Snap in OSU Math is the professor I'm talking about. He has a paper under review with Chris Porter that actually intentionally put questions on their final to try to see if Bart's Calculus 3 classes perform better on those questions than other Calculus 3 classes that did not have the VR intervention. The big thing we did is that in 2017, we had basically unfettered access to an entire 1,000 student, 500 student and 500 student introductory E&M class at Ohio State on the Columbus campus. So I teach at one of the regional campuses of Ohio State, but we got amazing access to one of the E&M classes, which we'll talk about in a second. Things that we learned from this, to me, I think the smartphones work fantastic for VR. Just from the first day that I used one of them, I just thought, wow, this is almost as good as a professional VR headset. There's so much that we could do with this. Let's figure out what we can do with the technology that already exists. I think if we did it all over again, and this tool did not exist at the time that we were building this stuff, if we did it all over again, we'd probably use something called WebVR or A-Frame. And that is, you don't download an app, you just, the student would open up a browser, the browser would go split screen and do 3D stuff in that. And that actually does work. In terms of research, and again, I'm not really invited here to talk about the research, but I do want to briefly overview what we did. So we had something like 500 students in spring 2017 and another 500 students in fall 2017. Not all 500 and 500 got the VR treatment, so we would often split them into 2 or 3 groups. So in spring 2017, we did something like where a third of the students had a VR visualization of electric fields, and a third had images, and a third had videos, things like that. And the students would all come into the Physics Education Research Lab at Ohio State. So that it was all sort of the same controlled environment. This is the largest controlled study in VR for physics, and maybe even more generally than that, VR and STEM. And I have to give credit where credit is due. This is Dr. Chris Porter helped to lead this, and Dr. Joseph Smith led the software development, but Joe also pitched in greatly to actually collect the data. So this is a huge amount of work. And then we also had undergrads and grad students helping us as well, who are on the papers as well. The products of just that year, so it's a lot of students, it's a lot of data, and so we've been publishing on that ever since. And so the first results were published even before we could do fall 2017, which was this PERC paper, led by Joseph Smith. We found some interesting results in terms of the way that student-reported video game play affected their ability to accurately answer questions in the VR environment that had to do with electric fields. So I think this Smith et al. I think got people thinking more about the kind of video games that students play. Porter et al. 2019 is another PERC paper. There were some mixed results, and you can kind of see for yourself in that paper. This is really Chris Porter's idea, the third paper, and it used the fall 2017. So from spring 2017, we kind of found overall there wasn't a big improvement from using VR compared to other media. We found that students who played video games benefited from it more than students that didn't, but overall, not a significant difference. Chris, who is familiar with the literature and knew that there's papers on visuospatial thinking that found that with training, people's visuospatial thinking, so for example, rotations, think of Tetris but in 3D, and people could be trained to do better at that. And so Chris had the idea that what if we just give the students a couple of extra minutes in the VR headset, again, smartphone-based VR headset, to acclimate, to give them some things to look at that might not necessarily have anything to do with physics, and then ask them the questions. Does that actually help them to answer these physics-based 3D VR questions better? So for example, directional electric fields in different situations. And the answer was a little bit. So it was a statistically significant effect, the improvement, but it was still true that overall VR did not outperform other media. It's not just the buckeyevr group that's finding that VR tends not to produce the learning gains that one hopes. There's also the Cornell group has found similar things for astronomy, and there's another group from MIT. Both of those are sort of studies that were smaller than ours, but we're all seeing the same lack of impact. An optimistic view is basically that if you look at clickers, there's a right way to use clickers and a wrong way to use clickers. The right way to use clickers is to show the students the question and ask the students to talk to the person next to them and try to figure out what the answer is. That has an impact. What does not have an impact is giving them the clickers, showing them the question, and saying, don't talk to anyone, just tell me which one you think is right. That actually does not have an impact, is my understanding. So VR, potentially in the same category, is that if it is going to be a killer app, we still have to figure out what's the right way to use it, and nobody has quite figured out the way to do that just yet. So that's kind of the optimistic view. But in any case, there's fun stuff that we have to share that we hope you like. And I hope that you'll reach out to me or Chris Porter or Joseph Smith. I think the upshot from this talk that you should take on this slide on research is that please invite Chris Porter and Joseph Smith to talk to your departments about the kind of research that we did on VR in introductory electromagnetism. I think that you'll be very interested and engaged with what they have to say. I'm co-author on all these papers, and so I collaborated with them at every stage. But there's no one better than Chris Porter than Joe Smith to represent these research results. So thank you very much for having me for this invited talk. I hope you enjoyed it, and I hope that you will go to buckeyevr and kind of check out the resources that we have. So thanks.